Regarding that, remember homework 3 due after the break, at which point I'll give you probably another homework, probably have another 3 to go at this rate. And exam, I think, is for the 8th, right? Yeah. So for the 8th of May. Last Tuesday, this Tuesday, we talked about boosting. And I thought it was a really nice class because we were very lucky to have Rob Shapiro with us, who is one of the main inventors of this technique. And I went through it saying this is an algorithmic technique mostly, having to do with efficient algorithms, not so much with statistics. So perhaps one of the main, or I would say the main algorithmic consequence of statistical learning theory that allows you to build efficient algorithms using simple rules of thumb. What I'd like to do today is talk about extensions of boosting to other paradigms. And if you remember, we talked about statistical learning theory and we defined what it means to learn in that model as learnability of a hypothesis class. Let's remind ourselves, so statistical learning. I'm writing it in shorthand notation. We define to say that hypothesis class H from features X to labels Y is learnable if and only if for every epsilon and delta there exists an algorithm such that for every epsilon delta there exists an m epsilon delta such that for every distribution over x plus y the algorithm takes sample S from D to the n and returns hypothesis which will be denoted by A of S from X to Y such that the error over the distribution of the algorithm is less than epsilon with probability at least 1 minus delta. So this was our definition of statistical learnability, and we argued we've seen one and only algorithm for statistical learnability, which is ERM, empirical risk minimization, which means just pick a hypothesis which classifies everything correctly, and we said that's going to be inefficient, or for the vast majority of cases, this is an inefficient method. It's only existential. And then we argued, okay, the balance that we get are pretty good in terms of sample complexity, but there is nothing algorithmic. Algorithmically, that's the main hard problem. And then on Tuesday, we talked about weakening this definition to allow error which is slightly below half for binary classification. So slightly better than random. Random, of course, is trivial. But as long as you can do slightly better than random, for the same exact definition, you can boost the weak learner by an efficient algorithm, which we saw. We saw a multiplicative weights-based method, and we talked about AdaBoost, to a strong learner. That was a very strong paradigm. Everyone remembers, right? And then people asked me, can this be extended? And we had a bit of discussion with Rob, and we talked about, okay, how can this be extended? What would make sense? So people, because it seems to be, well, not seems to be, it is known to be a very effective paradigm. Boosting is a very effective paradigm. And it would be nice to take this algorithmic paradigm and apply it more broadly, not only to statistical learnability, but to other settings as well. For example, agnostic learning, so do you really need, this is very strong. This means that you can get zero error for whatever you're trying to learn. Do I really need this realizability assumption that the error can be driven to zero? What if it's not possible to drive the error to zero? So there is a concept called agnostic learning. Agnostic learning is the cousin of statistical learning, or agnostic statistical learning. I can copy the same definition here and say that H is agnostically or statistically learnable if and only if same thing happens, but the error that I would require is less than the minimum age in the hypothesis class error plus epsilon. So same thing, but I don't necessarily need to compare myself to 0. Rather, I compare to myself to the best hypothesis in the class that I'm trying to learn. This is it. Any questions about what it means? This is a natural thing to define, because what if our hypothesis class, let's say the set of neural networks or the set of Python programs or the set of linear classifiers is powerful, but it's not large enough to capture all the intricacies of the data. We want to allow some error. Or what if my concept itself has noise in it? Maybe nothing learned. It has inherent noise in it. There's nothing and get 0 noise. You're sort of bounded by the inherent noise in the data. So this will allow you to be more noise robust. And you can ask, okay, can I do something in this setting? Because again, there is no efficient algorithm here in general. It's a hard problem, but maybe you can. Can we apply boosting here? Agnostic boosting, it's called. And this has been studied for a long time in the machine learning community. The answers here are interesting. I wouldn't say it's not closed. There's still interesting open questions here, as opposed to standard boosting. Any other suggestions for generalization or improvements? Yeah, Elijah?
You can apply some techniques from online convex optimization, since you've got something that looks like regret if you arrange the terms.
Oh, that is absolutely correct. In fact, for boosting itself, even in statistical learnability, we apply techniques from online convex optimization. Even though it seems unrelated, we just apply it as an algorithmic technique. And as Rob was saying, that was also the original way that boosting was devised. Somehow it's not being taught that way, but I think what I taught was closest in spirit to how originally it was devised. But regardless of the technique, let's say I'm looking for a target, which is a more general target than boosting in this kind of setting. What would it be? Any ideas? Where would you like to apply boosting to? You see what I'm asking? It's kind of I'm not asking you a technical question. I'm asking you where would you like to apply the concept of taking some weak learner, some learning method that is, yeah, Alex?
I mean, maybe just in the online setting.
Okay, very good. So maybe in the online setting. So my question is, I want to take some learner which is weak. It doesn't have this amazing strong properties, and improve it. This seems to be a nice thing to do, and we have a good technique of doing it via this game theoretic viewpoint. Can we generalize it further? So maybe online boosting. And online is inherently agnostic, right? All our online algorithms were inherently agnostic in the sense that we didn't try to get 0 regret. We tried to compete with the best in hindsight with some regret. We didn't try to get 0 loss. So that's what I'm going to talk about today, online boosting. And I should say this is something actually that was pretty recent. The results I'm going to talk today are simplification of results by my student Natalie Bruchin and another student, Karan Singh, who is a professor now at CMU, and myself, and Natalie is going to be professor next year. I don't know where, but she has a lot of offers. It's a nice thing. So let me give you motivation for why or why do I even need this online boosting? I mean, we had the online convex optimization. It's a very general approach. It's a very strong approach. And we get efficient algorithms. Inherently, everything is convex. You know, we have a very powerful setting that we're able to use to solve games and solve linear programming and all sorts of difficult things. where is the situation that we could improve upon? So let me give you a motivation. Suppose we're trying to solve prediction from expert advice. So you remember the problem, we have n experts, each of them is giving me advice, oh, you should buy, you should sell, you should do this, you should do that. And I choose to follow the advice of one expert, and then I get to see the loss of maybe all possible experts, or all possible decisions, full information, not bandit. You can ask also boosting the bandit setting, also very interesting. Natalie did a lot of work in that setting as well. But today, full information, so I have all information I need. Well, we have seen that we can get regret bound that behave as square root T log n. If we have n experts, and that the losses are in 0, 1 in a very general setting, very adversarial total setting. This is a fantastic regret bound, but what was the running time of the methods that we've seen? Do you remember the algorithms that we've seen? Hedge, right? Multiplicative weights, gradient descent, all of these methods. What was the running time? Yeah.
Well, it would be at least linear in the number of experts, right?
Correct, correct. So the algorithm Hedge, which attained this regret bound, it's the best algorithm we have seen for prediction from expert advice, and in fact, the best algorithm overall, has runtime which behaves linearly in the number of experts. It has a weight for each expert, then it scales it up or down, and it's to maintain all these weights and so on. Now, not too bad. I mean, you can think this is fine if you have some reasonable number of experts, but there are situations in which you can have many, many experts. Give me an example. Yeah?
All of the possible combinations of weights of the neural network.
So you think of every neural network with weights as an expert. I will get to it. Let me just answer Elijah's question first. That is an interesting point. But I would say that we somehow, I would say, solved even in the efficient representation of online convex optimization. So I would move to, instead of for every possible weight having an expert, I would bound a set of all weights. So weight for the first edge between 0 and 1, weight for the second edge between 0 and 1, and so on. And then you have a convex set of all neural nets that is succinctly representable by the number of weights. So your proposal would be to have, for every possible weight, have an expert by discretizing the space. That is exponential in the number of weights. I'm saying you can make it linear in the number of weights just by the convex parameterization. Okay? So I would say we talked about this kind of difficulty, and in fact we talked about it when in the online shortest path problem, maybe most prominently, and we moved away from paths to flow polytope. Yeah? You agree? You had?
Oh, I was just going to say each path through a graph.
Yeah, path through a graph. So again, I would say we solved that. We solved that by moving to online convex optimization from experts. Okay? But I could have talked about a more general phrasing here that is online convex optimization. Still, I mean, I would still depend on the dimensionality, the number of edges in the graph, or the number of weights in the neural network. You had some?
I was going to say, if you optimize over a non-convex set, then you haven't solved it, and you would need to do boosting or something.
Yeah, that is correct.
Yeah.
That is a good point. So one thing which I didn't prove to you, but I need to prove to you, is that non-convex optimization is NP-hard. Let's see how much time I have. Should I do it? Okay, let me do it real quick, okay? Did I prove to you that non-convex? I didn't prove to you, right? I should have done it. I was thinking to myself, this is a hole I left. I didn't plan on doing it, but actually there is a very nice proof, very simple proof, okay? So theorem, non-convex, and even quadratic optimization is NP-hard. Proof. So given graph G equals VE. Yeah,
So what is the decision problem here? So it's a decision problem, right?
I'm just saying quadratic optimization is NP-hard. There's no decision problem. Quadratic optimization. So what is quadratic optimization? You want to minimize or maximize f of x over x in a convex set in R to the D. This is convex. This is quadratic. Okay? So, yeah, is it clear what I'm saying? So this is kind of a basic building block of everything we're doing in mathematical optimization. And we usually do linear, sometimes convex. Why the heck did I move to convex? So let me show you, move a little bit beyond convex. It becomes hard and I'm kind of, Rohit threw me off track here, but I think it's important. Question? Let me just prove it to you because otherwise, I don't like to have a hole in the course. So I'm given a graph. Let me define and consider the max cut problem, which is known to be NP-hard. So in max cut problem, we're trying to find a partition, S and S bar, that are contained in E, such that maximize the number of edges from S to S bar. S union S bar is E. S intersection S bar is empty set. That's the problem. You're all familiar with it, right? Yeah? Everyone seen this?
V. Sets of vertices.
V. Correct. But everything else is fine, right? Yeah. V? Yeah? So let's define a quadratic program. So let xi belong to plus minus 1. And now let's try to maximize summation over all ij in E, 1 minus xi xj over 2. Okay, this is a quadratic function. Yeah? And then I also write xi is between minus 1 and 1. So this is a convex set and quadratic function. Okay? So, yeah, everyone agrees? This is a convex, the cube, very easy set, nothing too fancy. And quadratic polynomial, also nothing too fancy. And my claim is that this is equivalent to max cut. So whatever the maximum value here, I will get a cut in the graph and vice versa. So vice versa is easy. Take a cut, assign 1 to one side, minus 1 to the other side. You see that if the edges cross the cut, I get 1 minus 1 divided by 2, that's 1. And if the edge is on the same size of the cut, it's 1 minus 1 is 0, will be 0. Okay? The other way around, you can say the following: take any solution to this mathematical program, and in general, maybe xi is not 1 and minus 1, only it's 0.9. What are you going to do then?
Round up.
Okay, why is that okay?
Oh, I forget the proof. I just remember that.
No, someone prove to me. Why is the solution without loss of generality on the vertices of the cube? Yeah?
Well, I mean, if like we're saying, if we have a solution to this and it happened to be 0.9,
Yeah.
like, to go back to the original problem, like, if we only have a choice between 1 and -1, then like, I was going to say clearly, maybe it's not clearly, but like clearly going to 1 is better than going to -1.
I don't know about that. I mean, I agree something here is clearly, but not that this is clearly. So, but what I'm claiming is clearly is that the solution is always at the vertex of the cube. That if you have some points that are in the middle, you can move it to the corner and only improve the objective value. Yeah? Who sees it?
Does it have something to do with a gradient?
Yeah.
You,
Yeah,
it's not zero,
yes, but let's do simpler than that. Simpler. Yeah.
You have a
I'm
point
gonna-
inside the polytope. Cannot be optimal. Has to be on the edge of the polytope.
Why? This is correct. Why?
Because then the gradient cannot be 0. Like I think you can push it in some direction and gain from some direction.
Okay, okay, now we're getting somewhere. Why can you push it to some direction and gain? Yes?
And then you have to push it to the direction it's gaining until it goes to
But
the
why? Okay, all of this is true, but I didn't get the, Joshua?
So fix some number I and then consider the inner sum over the j.
Yeah.
Either like -1 or 1 will like basically like
Good,
optimize.
good. So if I fix all the variables except for one of them, I fix them, right? I have some number multiplying the variable. So it's either positive or negative or 0. 0 doesn't matter. And if it's positive, I move it to 1. If it's negative, I move it to -1. I only improve my objective value. Is it clear? So true, I can go by gradients and all that, but I like this elementary kind of consideration. Okay? So, proof by discussion. Okay, so we discussed. Okay, we discussed it. You can all. I think it's a good exercise for you guys to make it formal. I don't. This is kind of. It's not a hard proof, but in terms of difficulty, like what I would expect from you, it's not some. If it's homework, yeah, maybe I'll give it to you as a question. In the exam, I don't expect you maybe to come up with it yourself. But after I told you now the solution, I do expect you to be able to write it down formally. Okay? Just in terms of like what I expect you to do. Yes?
Why does the theorem say non-convex optimization?
Oh, good question. Who can answer? Yeah. No, Joshua, you will say enough. Yeah, you?
Well, I was just gonna say that's not a convex function because it's negative, but it's not this way, it's this way.
That is correct. So this is not a convex function. If you take the Hessian of this function, you will see that the diagonal entries are all 0, and the non-diagonal entries are sometimes 1, sometimes whatever, -1, and it's not a positive semi-definite matrix. So it's not a convex function.
I see, but the region is always convex.
The region, well, in this case, the region is convex.
So, but it doesn't.
Well, it's NP half. It does. I mean, it's what I'm proved to is even stronger. So what I showed to you is, okay, I showed to you in lecture 3, 2, whatever, one of the lectures, Rohit also showed to you, convex optimization is solvable efficiently by gradient descent. We proved that, yeah, from scratch, in class. Now you may ask, wait a minute, is this necessary? People did ask me, what if something is not convex? I'm telling you the following. Even if the set remains convex, even if the function remains smooth and quadratic, it's like the simplest thing you can be non-convex in. Linear is always convex. Quadratic, one more degree, and that is a bit non-convex, boom, it becomes NP hard. So it's important. I should have maybe said it previously, but I'm happy we kind of digressed the lesson and proved it now, so that you see that everything we're discussing really is inevitable. I couldn't have gone another route, if I go slightly off track, it becomes NP hard. So I have to go back to convex land, okay? Questions? Yes?
Just a nitpicky question. When you write bar on the top right there, what about R is quadratic?
R is not quadratic. The function, the objective function is quadratic.
Okay.
Yeah. R is the real numbers.
Okay.
So this is an R to the D. It's not 2 here, it's D.
Oh.
D.
Not bad. Thank you.
Kara, you had a question?
I was just wondering if this is true for like all non-convex objectives or just this?
No, it's not true for all non-convex. There are plenty non-convex functions that are solvable in polynomial time. For example, take any non-convex function over the cube, multiply it by 0.001, and add to it f of x equals x. So now the x direction is going to dominate, and then you're going to solve it. So it's not to prove a lower bound. I'm happy you asked me. When we prove lower bound, which we didn't do so far too much in the course, I don't want to prove to you for all such cases something is bad. I just prove there exists a situation where something goes wrong. This is different from an upper bound. The upper bound we're saying every time this function is convex set, and all the conditions that I mentioned are all, my algorithm is efficient. Okay. More questions? So I like this proof. It's a very revealing, I would say, proof, because it shows you if you step outside convex land, you're in trouble. And how did I get to it? I got completely sidetracked by Rohit's question. will try to get me to talk about non-convex boosting, but I agree with you. Maybe if you have non-convex objectives, that is a good place to try to plug in boosting. I totally agree with that. However, you have to keep in mind that when you want to solve non-convex objectives such as this, then you're inherently shooting for something which is NP-hard. So if your algorithm is efficient, it probably means that your oracle is NP-hard.
Yeah.
Okay. Good. So let me ask the question again before I got sidetracked. When would it be a good idea that we have such a huge decision set, such a large number of actions that I want to apply something other than hedge or online convex optimization, which you also know. That's part of our toolkit now. You all know that. So it's a way to efficiently solve problems that are structured. Yep.
Sorry, I was going to ask a question, but I think that whoever answers this question is going to answer my question.
Okay, so let's go with my question then. Kara?
I guess you were saying when the dimensionality is really high, so like the stock market has lots and lots of stocks, so there's like an expert for each stock.
Yeah. Okay, that's a good, maybe for every strategy over trading, right? So you have a lot of stocks, dimension is high, and a lot of strategies maybe. Yeah, that would be a good example, because the strategies are not structured necessarily. So I have trader A, trader B, trader C, God knows what they're doing. I don't know what they're doing, they're black boxes. They operate in a small space, but it's not clear how this will help me because they don't have any structure that I can exploit. This is different from, Kara's example is different from paths in a graph. Paths in a graph I can exploit. I know that they have the structure, they live in the flow polytope, there are the vertices of the flow polytope and all that. This I don't know how to exploit. That's a good example. Other examples? Yes, Taya?
Could it be like recommendation systems?
Fantastic. Okay, fantastic. So, recommendation systems. Many times, it's a particularly nice point. And I would generally say contextual problems. So, contextual learning. This is a good example. Did people hear about contextual learning here? Contextual bandits? Did someone hear about it? This is a model which you heard about it.
Hey, you told me about it.
Okay. That doesn't count. But I guess Go knows about it. So there is, let's think of a setting in which every iteration I have a context to make my decision. It's not just a vanilla decision. And this can happen because of, for example, recommendation systems. I have to make a decision whether to recommend a movie to a person or not. And I know something about the person. They clicked like, dislike on all the Netflix Superman movies or whatever, and I kind of know their history of likes. And therefore I can make a kind of an informed decision. Another example would be in social media, these companies have a lot of data that they collect over the users. So if I have an Instagram or Facebook account and I click various things, and that history of clicks is very revealing. Maybe they want to recommend to me, oh, this person likes sushi, doesn't like something else, right? So I want to give him the cooking, whatever, classes. Somehow I get a ton of cooking on Instagram every time I see food. Figured out I like food. So there is a contextual decision to be made here. And the way you can model it is you have a distribution over contexts. And these are maybe AT, these are vectors in R to the D. And then at time t, you see AT and predict maybe some xt, which let's say is in 0, 1. So far, same as prediction from expert advice. But what I like to compete against, I want to compete against the best policy. Policy is a mapping H from context to decision. You think of it as some hypothesis class. So usually there are many more policies. You can there are only 2 decisions, maybe 0, 1, but there are many ways of making these decisions depending on the context. So this is a natural situation where you have many more decisions than many more options, possibilities to make a decision, because you would like to take the context into account. So here you can think of there are many, many different hypotheses or possibilities to make decisions, taking into account the past recommendations or past context. Is this clear? Because now I'm considering all mappings from set A to set B, not all decisions in some convex set. Yeah?
Is this related to swap regret?
A little bit, yeah. Swap regret is a really bad notion. I'm recorded here on YouTube. I don't want to say too much about it. It doesn't give rise to efficient methods, and in my opinion, it's not useful. But I'm going to stop here. I already got in trouble with statistical learning. But contextual learning is a fantastic framework because it allows you to capture problems in the real world, such as recommendation systems, such as prediction in social media, such as reinforcement learning. The context in reinforcement learning will be the state that you're in. You have some states of the world. In every state, you want to make a decision. Now, do I go left or right? That very much depends on the junction I'm in. Okay, so you're trying to compete with a policy. Yes?
Can you frame this in the online setting where like all your contexts are just like previous, I guess.
The contexts are online? Yeah, they could be. Yeah. So I could talk about a sequence of context. Yeah.
I feel like is there any differentiating factor between previous as like a sequence of like I guess like previous contexts versus like
Distribution?
yeah.
Not significant from my perspective. Whatever you can do in the distributional world, many times you can do in the online world also. So there are some small differences in terms of possible rates that are achievable and so on, but in my opinion, it's not significant. I always like I thank you for saying that because I prefer sequence to distribution. Then there is no statistics here. Yep.
Are there any restrictions on the types of policies that you can?
Oh, absolutely. So this is maybe belongs to some class A. Okay, and age is huge. So this is where I want to make use of boosting because I could have run hedge on set age, but that's going to be a problem because a computational problem. Statistically, it's not a problem. I'll still have square root t log age regret, and that will recover the statistical learning rates that we have seen. But computationally, this is not well behaved because I need a weight for every possible age. And there is no structure to help me here. There is no convex set of age, nothing like that. Just an arbitrary set, okay? If there is structure, I can make use of it by online convex optimization, by the language of mathematical optimization. Clear? Yeah?
Wait, sorry, is there like a law, so like an actual X of t?
Absolutely, yeah. I mean, you make a prediction X, and then you want to compete with the best age in hindsight. Let me now define it more rigorously, but it's the usual thing that we had. You make a decision, and then you suffer a loss, and what you compare against, you don't want to compare against the best fixed X, you want to compete against the best fixed policy, okay? Yeah?
Is there any structure between 80 and 80 minus 1?
No. You can look at all sorts of refinements. So last night I was pretty happy. I looked at well, it started with a bit of unhappiness. I looked at my book at chapter 12. I was not very happy. It was kind of too complicated. So I thought I want to teach you guys something which is simpler, kind of a bit more, maybe that I like to fit my classes in 1 hour and 20 minutes and kind of wrap up the full theorem. So I'm hoping to do that. So it will be a bit simpler than the book discussion. Questions? All right. So this doesn't appear in the book, but if you want to take notes, there is a more general version in the book, but I'm going to give a simpler version now. Okay? And if you want to see all the details with more complicated and more rigorous, this will be rigorous, but if you want to see more detailed constants and so forth and more general settings, the chapter 12 in the book has that. it subsumes what I'm going to show you now. I think this is simply what I hope what I'm showing is the crux of it. So the first thing I need to say is what my goal is in online boosting. In online learning or online convex optimization, I want to work in OCO. So I want to do boosting for OCO. What is a strong learner? Strong learner is a regret minimizer. Think of the case of the vanilla OCO. So I have x1 up to xt. They're all chosen from a set k, which is a subset of r to the d. Then I have this sequence of loss functions, f1 to ft, from k to the real numbers, or if I'm going to assume it's from r to the d to the real numbers. And usually we're trying to minimize regret, right? So strong learner has summation ftxt is less than the minimum x star, summation ftx star plus regret. And this usually behaves like square root t, either square root t log d or gd square root t, depending on the algorithm. Or Newton has log t and so on. This is kind of sublinear in t. So what I'd like to do, I would like to obtain this sublinear regret, but without explicit introspection into the set K. If I have prediction from expert advice, I do not want to depend on the number of experts. Okay? That is a disaster for me. So what will be a weak learner that will allow me to accomplish that? Who can think of a definition of a weak learner? Well, you're restricting what the algorithm is allowed to do, okay? From my perspective, the algorithm can do whatever it wants. If we take the analogy to boosting, I don't care what the weak learner does. He can do whatever it wants, but I had a weaker guarantee that it provides me. And the idea was, okay, if it only gets a roughly better than chance, probably there is a simple way to do it, like a rule of thumb, okay? So I would ask you guys to think in that respects. What kind of guarantee should I expect from my weak learner, and not in terms of what it does? If it wants to do something very complicated, go ahead. Yeah, Kara?
Maybe something like does a little better than the average expert or something.
Okay, I like that. So, okay, let's do that. So let me define a weak learner this way. I think you have it right. So summation ftxt will be less than, and here I will put here gamma times the minimum x star, summation t ftx star, plus 1 minus gamma. Gamma will be some gamma weak learner. That's going to be the age of the weak learner. ft of x bar. X bar is going to be maybe the average point or some random point in K, plus regret. So good. I'm taking Kara's suggestion, okay? So this algorithm is able to do the following. On every sequence, it's able to do better than this x bar. X bar, I define it to be random point in K, or if you will, center of mass, or any other point that you want to fix. Yes?
The sum over t also applies to the second term.
Yes. Yeah, you're right. So what's the easiest easiest way to correct what I did. Let's put a summation here. Yeah.
Sorry, just to be clear, we still have that K is convex in this?
Yes, K is same as OCO. K is convex.
Okay.
Loss functions are convex. I'm not going to non-convex land. Still staying in convex land. But I do want to solve my contextual problems and large experts, and I want to do it efficiently. And I don't want to access even my convex set. The only way I will access the convex set is via this weak learner.
Is it clear how this maps to the contextual learning case?
I think so. I think so. I think that basically you can think of X as a hypothesis in your hypothesis class, and then you're choosing a hypothesis that wants to compete with the best one in hindsight. And the reason I'm not taking into account the number of hypotheses here is because I have a weak learner that automatically gives me some guarantee compared to the best hypothesis. Okay? So actually, OCO captures contextual learning. You don't need to do any change. It's already as good as contextual. It's just an example. It's a subcase of OCO where my decision set is very large. It's not an example of a different setting. It's subsumed in OCO. So when I say boosting for OCO, this includes, OCO is more general, including contextual learning. That is a very good question, Elijah. Thank you. Yes?
But how can we define H to be convex?
We don't, but prediction from expert, we can take the convex hull, for example, like prediction from expert advice. Okay. Or it could have a natural parameterization or many options. Okay. So that's why I started from prediction from expert advice. Maybe the easiest way to think about it is experts. What would be the average expert for prediction from expert advice? What would that be? Yes? Uniform distribution, very good. Questions? Now, I'm going to assume, let's assume, for simplicity, even though I don't have to, that ft of x bar is 0. So I'm just going to assume it's 0. The average loss is 0. Yeah?
Sorry, I wanted to ask a question for before. Can I ask it now?
Yeah.
Is this the only way to define a weak learner? Is it the only way that the people have to define a weak learner, or is it another way?
You have another idea to define it, or just asking for general knowledge?
General, because I was thinking of another way, but this also makes sense, but I was thinking of another way.
What's the other way we're thinking of?
I was thinking of like, you can think of a learner like it has some linear regret on a subset of like the time until now. And then you can combine them somehow.
So that learner is only awake during a sub-interval in time. There is such a notion, but it's not used for the same purpose as what I want. And in fact, you need a coverage, clearly you need a coverage, and so on. So the other issue with that is why would the times behave differently? Some subsets behave differently than other subsets, right? So if you're able to do, because we're considering an adversarial setting, why would your expert be awake only subset of the time and not in other subsets? There is a reason, but that has to do with dynamic environments. So the motivation is totally different. In short, this type of setting was considered for a totally other motivation, and it's not directly related. In my opinion, it's not a good fit for boosting, for computational reasons. It's good for dynamic reasons. There's some other question here? Yes?
I was just going to ask, what's the bound on FT of X? And can it be negative?
Well, yes, because if it's only non-negative, this is even a stronger guarantee than just a regret. So I'm assuming, assume ft of x is in negative 1 to 1. That's it. So I'm assuming it's between negative 1 to 1, and therefore this is a weaker, if let's say gamma is 1/2, this is a strictly weaker guarantee than regret minimization, strong regret minimization. Otherwise it's not weaker, it's stronger. So, and it's impossible to do. It's only possible to do when you have a weaker notion, and that requires negative losses. I couldn't define everything as positive losses. It's much more elegant this way. So trust me when I say it's more elegant this way. Otherwise, I would have needed to take gamma to be a number larger than 1, and the whole thing would have become more messy. But it's analogous. You can do that too, using the same technique that I'm going to describe. More questions? Okay. So I'm going to assume this. I'm going to assume that the losses are in -1 to 1. I'm going to assume that the FT functions are beta smooth. This is not a requirement. I could have made it work without the smoothness assumption by the technique of randomized smoothing that we discussed when we talked about bandits and Rohit talked about optimization. But it will make my life simpler. So I'm going to assume it. I'm going to assume FT is defined over R to the D, even though that doesn't have to be the case in OCO, but makes my life easier. And I'm also going to assume that projecting X onto K minimizes FT. So FT obtains the minimum on K, which is, again, not a requirement in general OCO, but I'm going to assume it since it makes my life easier. So all of these things can be relaxed and removed, but I want to give you the simplest version. So let's see the algorithm, which is called online boosting.
The last assumption means that for any x outside of k, projecting it will give the minimum, that is f of
Not the minimum, but it will be smaller than remaining outside. So moving towards k, for example, let's say k is this interval, so let's say this function. Okay. Yeah. So if I move from here to here, it's not the minimum, but it's smaller. Okay. More questions? Okay, so let's look at the algorithm. And the input is our weak learners W1 up to WK. Then I'm going to do the following. So I'm going to initialize x0 to be 0. Let's say 0 in the set, or arbitrarily. And for t equals 1, 2, and so on, up to t, I do the following. So I need xt of 0 to be 0, and I do another loop for I equal 1, 2, up to k. This is going to be the difference from usual OCO. We only moved through t and did a simple gradient update. I'm now going to call the weak learners. And I'm going to call all of them. I'm going to call many weak learners. So I define xt of I to be 1 minus eta I xt of I minus 1 plus eta I of what the weak learner, ith weak learner gives me at time t. This is wi at time t. And then after the for, this is end of the for. Predict xt, which I define to be the projection of xtk. And now I need to update the weak learners. So wi is going to be given a loss function, which is ft of I, where ft of I is going to be the gradient of ft of xti dot x. It's a linear function. That's it. End. Any questions? Yeah?
Sorry, I might be confused. It looks like you're predicting the prediction given by the kth expert every round. Am I misreading this?
No, yeah, you're k. There are k. Yes, this is correct. So there are k weak learners, and what I'm doing two processes. I start from 0, and every iteration, I'm running all the weak learners to update my point, some intermediate point. Whatever it reached at the end, I'm projecting, and that's what I'm deciding. Okay? So I'm using all the weak learners in succession, every iteration. It looks kind of weird maybe, but there is a reason for that. I'm not using one weak learner. I'm using k. They can all be the same. I don't mind that, but they're applied to different functions. So I'm using here k weak learners to make my decision.
So is this like eta I sort of what's determining how you mix between the weak learners?
So eta I is going to be 2 over I. Yeah. Just a fixed number. Yes, that's the mixing rate. And for 0, it's not defined. 0, it's 1. Okay. Yeah.
So if eta is like 2 over I, doesn't the level of the weak learners matter though?
Yeah, it definitely matters. It does matter. You're asking if it matters? It matters, yeah. I mean, they're given, each one of them is given a different function. Okay? I guess this might be the most sophisticated algorithm you've seen so far. Maybe Newton is more sophisticated, I don't know. This kind of a sophisticated algorithm. Yeah?
What's the sequence of endpoints that each weak learner sees? Is it just like a subset of the, does each weak learner see like what the previous weak learner saw plus the point previous weak learner?
What's your name, remind me?
Jeff?
Jeff asked what's the sequence of points that a weak learner sees. So remember what a weak learner and a strong learner are. Both of them are algorithms for online convex optimization. They don't see points, they see functions. They see loss functions, and then they predict a point. So they see loss function, predict a point. They see loss function, predict a point, and they guarantee low regret. What each weak learner, what I need to give him to generate a point is a loss function. And the loss function I give him is this, ft of I. At time I, at time t, the I weak learner gets this function, which is a linear function. It's determined by the gradient of ft at xti times x. Make sense?
Do you not see the sequence of points like x1 to x?
Well, are you asking what's the guarantee of the weak learner? I can write.
But like, don't you have an input like the sequence of points x1, x2?
No, it's not an input. It's not an input. This is shorthand. In the setting of online convex optimization, the way it works is we predict an x1, see an f1. Then we predict x2, then we see f2, and so on. That's the way it works. I don't need to rewrite this, right? Everyone remembers that? So it's an adversarial repeated game. Okay, it's not all known ahead of time. Yeah?
So why are we
you'll see in the analysis. So the idea is that each weak learner learns more from the previous one. Just one is not enough. You'll get if you can apply the weak one, you'll get gamma. That's not good. I want to reduce weak learning to strong learning. I want to take this weak learner and boost them to become strong, right? I didn't write what I get from the whole thing, so let me write the theorem. Is that summation t ftxt minus minimum x star summation t ft star, the regret of this algorithm is at most t over root k times beta times something plus, I believe, regret. So whatever the regret bound of the weak learner algorithm is, that's the regret I will suffer here. There is another 1 over gamma here and here. And let me put an O here to hide factors having to do with gradient and dimension. Yes?
So you control gamma here, so you can make the square root of t, so you get something here?
I don't control gamma because gamma is part of the weak learner definition. That's the edge of the weak learner.
So this is not no regret.
Well, what do I control here? Good question. What do I control here to get sublinear regret?
Either step size.
No, step size is 2 over I.
Okay.
Yes, K. The number of weak learners. So it will increase my running time. The more of them I have, the more running time I pay. But if I take K to be T, this will be square root T regret. But notice, the running time doesn't depend on the decision set at all. There is no age here or n or number of experts, none of that stuff, okay? So that's the big deal. If I have infinite, whatever, 2 to the 100 hypothesis, that doesn't come into the running time. That's the main crux of that's the benefit of what I'm doing. And this is similar to boosting. Similar to boosting. Yeah.
So basically it's a trade-off between compilation and regret.
Correct.
And is this, do you know if it's tight, this one? Or can we get a better dependence on K?
It's tight in some settings, but I would say it's not known in general. Yeah?
For the second term, when you say regrets of T of W, which W is that, like, which weak learner is that?
Yeah, this one.
Oh, in general?
Yeah. Whatever weak learner, this is a reduction. Reduction takes a weak learner, has regret 5, it's going to be 5. Has regret square root T, it's going to be square root T. So whatever it guarantees to you, that's what you're going to get. Yeah?
Is it in general easy to find weak learners that don't look into the set K?
Ah, very good question. What do you folks think? Is it easy to find a weak learner? The way I've defined it? You can ask the same thing for general boosting. So is it easy to find a weak learner? The answer for boosting, and also from here, is that in general it's impossible. Because you're trying to solve a very hard problem. Okay, so you're trying to get sublinear regret over 2 to the 100 experts without counting the number. How on earth will you be able to do that? Let me even give you an example. Let's say that I just have binary classification and the labels are generated uniformly at random. How can you do better than random? It doesn't make sense that you'll be able to do better than random at all. It's basically there isn't a weak learner at all for that situation. It's even worse than usual boosting. Nevertheless, there are situations in which you can imagine that this will hold. For example, in contextual learning, maybe someone tells you, I've invented a new algorithm, it looks at all the preference of this particular person, it looks at all the movies they've seen, and I can really do much better than random. This person I know likes drama, I'll give him a drama movie, whatever, some intelligent kind of psychological research, and they can do a good decision based on the history. Social media, Instagram feed, whatever it is. Do you believe it does better than random? Yeah, probably does better than random. So that might be a good way to model it. It has a statistical assumption in it as well, not only computational. So in general, actually, this is impossible. But it's still an assumption we're willing to make for the sake of efficient computation. Yeah.
So I want to understand the connection between gamma weak learning and doing better than random.
Uh-huh.
So doing better at random requires that gamma be proportional to how much better the minimum is
Yeah.
to like random.
Yeah. If the minimum is the same as random, you cannot hope for this to happen at all. Okay? It assumes something about the sequence, actually, the fact that you can invent such a weak learner at all. This is different from statistical boosting. Statistical boosting doesn't assume that, but it assumes that you can do gamma margin better than random. Maybe also for some data there is nothing. The labels are random. You cannot do better than random. Okay? That's also a possibility. So in general, look, the hedge algorithm, going over all experts, giving them away, doing multiplicative updates, you cannot beat it in general. So you can prove that. There could be an expert, which is fantastic, and if you don't see what it's doing, you don't even see what it's doing. How on earth would you be able to compete with it? That's what not paying computational price proportional to the number of experts means, because you don't even have the information from all of them. The only information visible to you is from the weak learner. Okay? You guys are asking good questions, and the reason it's bothering you is because indeed, in general, weak learning is as hard as strong learning. That's what boosting shows you. It's as hard as strong learning. You cannot expect it to be any easier. But nevertheless, our intuitive expectation is that it is easier. Like you remember I showed you the bitmap example of MNIST. Yeah, these bits determine 1 and 0. Maybe not in general, but for the digits that we're trying to classify. Or there is some decision tree that can do better than random. More questions? How about I prove the theorem? So I prove the theorem and then we'll have more discussion if people want. So let me define delta I to be what the ith expert is doing in terms of the rate. So t equal 1 to t, ft xt I, ft x tau. And remember that I assumed that this f is smooth. It's a smooth function. Okay, let me write what it means. So this equals summation over t. Here I have f of xti plus eta I I must have missed the gamma in the algorithm definition. Yeah, I did. Should be one of the gamma here. So eta 1 over gamma ti minus xti minus ftx star. So the move from here to here is y. Why did I make this transition? What did I do here? Yeah.
You subtracted enemies because with this, like the return
Well,
on the gradients.
I just wrote what xti is here, okay? Xti by algorithm definition is this. 1 minus eta, you see? 1 minus eta, blah, blah, blah. So it's xt I minus 1 plus eta times this thing. Okay. That's all I did. This algorithm definition. And now I can use smoothness. So ft xt I minus 1 is ftx star plus eta I gradient f t xt I minus 1 minus gamma w t I minus xt I minus 1. squared beta over 2 times 1 over gamma gamma ti minus xt I minus 1 squared. Okay, what did I do moving from here to here?
Well, I mean, you said earlier, but that's just beta smooth.
Yes, exactly, beta smooth, okay? I do Taylor series, second order, okay? I moved from, I developed this around xti. So I developed this point around xti, minus 1, yeah.
Should that be an equality?
And I think it should be inequality. So smooth the smooth inequality, yeah. If it's a quadratic, it's equality. So beta smooth function means that the Hessian is bigger than beta identity. So that's why I have here the beta over 2 times the quadratic difference. Okay. Now, let me write what I obtained. So what I have here is the following. And if delta ti less than summation over t of all of this things. So this is basically delta ti minus 1. That's what I have here. Plus summation over t. And here I have beta I 1 over gamma fti negative ti minus ft xt minus 1. Plus summation over t, beta I squared, beta d squared over 2 gamma squared. This is the diameter of the set. So what did I do here in this transition? Yeah.
I mean, you just pulled out the delta I minus 1 from there.
Correct. Correct. I call it delta I. I replaced this quadratic by the diameter. Basically, I didn't do anything. Right? I just kind of tidied up the term. Good. So now, but I did one small thing. So I moved from gradient at xti minus 1 times these to the actual function value. And why am I allowed to do that? Convexity, and also that's how I define the function to be. So I define the function ft of I to be the gradient times x, okay? So by the
Convexity.
well, it's also true for linear is convex. So this is all
Linear,
yeah.
It's the definition of the function.
Definition and convexity, both are true. Okay. Yeah. Okay. So good. So let me make the main transition here. This is at most delta I minus 1 plus summation t beta I. And here I'm going to write the following. So ft of x star minus ft of xt I minus 1 plus summation t this thing, beta I beta d squared over 2 gamma squared plus should be regret. Eta I regret. Regret t of w. I believe there is a times 1 over gamma. So what did I do here? This is the main transition. Yeah.
Is this by the regret boundary later?
Exactly right. So notice I replaced this, right? This is less than. I know that fti is less than ft of x star times gamma, which is the 1 over gamma plus the regret. This is where I use the weak learning. That's all I did here. Okay? Yeah?
Should that eta I be squared?
Where?
The second.
Yeah, this is correct. Yeah, thank you. So this is my weak learning. Very good. Now this This is just negative delta t I minus 1, right? That's what it is. So let me write what I get here. I get this is equal to delta t I minus 1 times 1 minus eta I plus eta I squared times all sorts of things that are like beta d squared t over 2 gamma squared plus eta I times regret. Okay. So what I got here is an expression, recursive expression of the form delta t I is less than 1 minus eta I times delta t I minus 1 plus eta I squared times all sorts of stuff plus eta I times regret. Yeah.
Should there be a over gamma on the regret?
There is, yeah.
You mean on that line?
Oh, good. Okay. So this regret, remember eta I is like 1 over I. If I sum up over all i's, it's not going to be a big number. Okay, it's going to be also the regret times log t or something like that. I can also pull it into the expression. Whenever I have a recursion of this form, so this is just a mathematical, from this we're done. This is just like a mathematical statement now that basically whenever we have such an expression, forget this for a minute, this means that delta tk is less than basically this expression over here, let's call it a over k. That's what it's going to be. So this, when I pick eta I to be 1 over I. So this is a mathematical recursion. Let me write this in more detail. So, math lemma so this is in order to bound the last expression. Whenever I have a quantity ai less than ai minus 1, 1 minus eta I plus eta I c, and I choose eta I to be 2 over I, or minimum of 2 over I and 1 to be more precise, then ak is less than c over k. Maybe 4c over k. Okay? So this is a math lemma which you can prove. This is just a recursion. I don't need to go through it. And this will imply so from math lemma and final equation we get that the regret of the algorithm, which is summation t ftxt minus ftx star, this is at most summation t ftxtk minus ftx star. Why is that true? Yeah.
Isn't it just because you pick one?
Yep. That's what I use, right? I use the projection. So this is projection. I assume projection reduces my value. Projection. And this is basically delta K, and this is less than O of, and we'll have T over square root of K plus regret. So the square root of K, I even showed you with K, but if you balance out the terms correctly, it will come out to the square root of K. Okay. So I believe for smooth functions, I even get a stronger. I get divided by K, but for non-smooth, I think there will be a square root K here, if I need to do random smooth. Good. So that's what I wanted to show. And a bit of discussion. We're almost done. We're almost over time. Oh, okay. Any questions? We're kind of almost over time here. Yeah?
I guess more of a conceptual question.
Very good.
How, suppose like you're trying to come up with this, how do you see something like this in a proof? Like, how do you see the recursion?
That's a very good question. Edward, right?
Yes.
That's a very good question. I'm glad that we ended with a conceptual question because we're almost out of time. I think this would be a very hard thing to come up with on its own. But historically speaking, we have been working on an algorithm called the Frank-Wolf algorithm. It's an optimization algorithm that has a very similar structure that kind of linearizes and does these iterative steps. And that's where it came from. So it didn't come out of the sky. I don't think we would be able to devise it on our own. But it came out of some other method that we worked on. So this was in Natalie's PhD thesis, and she was looking at various variants of the Frank-Wolf algorithm, and that's how it kind of got applied to boosting. It's not a great answer, but it's not, we found kind of the right tool to use in this situation. I think otherwise this would have been hard to come up with. Yeah, and you're right to point that out. Any other, I'm not going to answer questions about the math because we're over time. Any other conceptual questions? I can answer maybe one. Okay, have a great break, and I'll see you after the break. Hi.
Math question.
Yeah.